Welcome to EDU World Space.
Okay, in this problem we have a fiber optic cable with diameter D equal to 750 micrometers and has a length of 1 kilometer. And we have two rays traveling down this fiber optic cable. One travels just along the axis, we call this ray A, and the second, as is in the case of a real fiber optic cable, travels at some angle and is bouncing off the walls of the cable. These multiple deflections occur before it gets to the end, and it's asking to find the change in time it takes for both these rays to reach the end of the cable. So we're assuming that the medium of the cable has an index of refraction of 1.465 in both cases, and we're asked to look at case A, where the outside medium for the cable is air with index of refraction of 1, and a second case where it has an index of refraction of 1.460, and we're finding delta T in both cases. So to start us off, we're going to be making use of Snell's law. Snell's law in all cases says that for refraction, N1 sine theta 1 for the incoming light is equal to N2 sine theta 2 for the refracted light. For a critical angle, for internal reflection, which is definitely what's occurring in a fiber optic cable, it's always the case that the critical angle, or theta 2, is equal to 90 degrees. So theta 2 is equal to 90 degrees. So our sine of 90 degrees just becomes 1, and we're left with N2 over N1 equals sine, we'll call it theta C. This is the same as theta 1. It's the critical angle for internal reflection, total internal reflection. So we're going to make use of this in a second. Now to find the delta T, the difference in time between the two rays, the one traveling just down the axis, the one that's reflecting, it's obviously defined as TB minus TA. And these times are really just determined by the speed of light in the medium and the length of the path difference. Well, yeah, the length of each path. So we have the length of ray B over its speed minus the length of ray A, its path length, over the same V, because it's the same medium. So they're traveling at the same speed. Now, what we can do here is if we go back to the picture, take a look at this. The only difference between these two rays is that that ray B is traveling a larger distance because it is going at these diagonals, obviously. So we can use some trigonometry to determine what that length is. And I would suggest that length is going to be length A over sine theta C, which means that the first term becomes LA over V sine theta C, the critical angle. And our second term is the same. And we can do a little bit of more simplification. Pull out some stuff. The speed of light is just C over N1. And then N1 over N2 minus 1. Great. And I'm making use of the fact that the speed of light in the fiber, so for both rays in the fiber in this medium, the speed of light is reduced, and it's equal to speed of light in vacuum over the index of refraction in the fiber. So I should write that here, that the speed V in both cases is just C over N1, which I substitute in here. So when I do the numbers, for case A, we have a delta T of, let's plug in everything we know, 1 kilometer times 1.465 over just speed of light, 3e to the 5 kilometers per second. And then we're multiplying by this ratio of indices of refraction, 1.465 over 1 minus 1, and that crunches down to 2.3 10 to the negative 6 seconds. It's a really small number, really small change in time, which is good. It says that a fiber optic cable can operate and essentially transmit information at the speed of light with very little difference because of that small angle of refraction. If we repeat the same thing, but we now replace we now have N2 equal to 1.460. We do the same calculation. We end up with delta T equal to 1.7 e to the negative 8 seconds. So it's even smaller. So in other words, the difference in time is negligible, and it's approximately the speed of light. And that's it.